What can I help you with?
I wanna go back one more time for the case three review. See?
Okay.
Just give me a moment. Let me get my pen and copy.
So which problem on the test three review would you like to look at?
Mm-hmm. So, so is it the um, question number four, the
Question
A?
number four.
A.
Number 4A. Okay, great. Let's look at that. So we're going to simplify and show work for credit. So what we have is, oops, n minus 2 factorial. No, is it n plus 2? It's n plus 2 factorial divided by n minus 1 factorial. Is that it?
Yes. And then the where n greater than or equal to 1.
Yeah, we have to have any of these expressions be 0 or larger. So the smallest n would be 1, right?
Yes.
Because
The
of
n
n,
is 1, right?
what?
The n is 1, right?
It's greater than or equal to 1. Because if n was smaller than 1, let's say n was 0, then 0 minus 1 would be negative 1 factorial, and that's not defined. The
Yeah, that's
low,
why I was like thinking, uh, the
it's
I
not a
use one
sequence.
instead of it. Mm-hmm.
It's not a sequence. It's just that this expression is only defined if each of these quantities that is being factorialized is at least as large as 0. There is no such thing as a negative value factorialized. That's the
Okay.
only reason we're saying this. That's nothing really deep going on there.
Right.
Does that make sense?
Yes, because I use the one. That's why it's going to be like 1 minus 1 will be like 0. So,
Yeah, well, 0 factorial is defined.
mhm.
0 factorial is defined to be 1. And then n factorial is defined to be n times n minus 1 factorial for n greater than or equal to 1. So this is the actual definition of factorial. 0 factorial is defined. It is 1.
Mhm.
But you can't just plug in n equals 1. N could be any value greater than or equal to 1, okay? In other
Okay.
words, what we'd like to do when we look, to create an answer is we just like to understand that we're looking at the very general situation where it's n plus 2 factorial over n minus 1 factorial for values of n for which this expression is actually defined.
I think we can use 3.
No, you cannot use a specific value.
Uh,
This
and
is going to be true for all integers n greater than or equal to 1. This is a for all kind of situation. We want to try to figure out what this is equal to no matter what value n is. Now you can look at some specific values. I don't think it's going to help you that much though. What will help you is to realize that n plus 2 is larger than n minus 1. If we look at the integer number line to try to understand what's going on with the integers. So if we're looking at z, and here's n plus 2, then what is the integer right before n plus 2?
uh, n plus 1,
Good. And what is the integer right before that?
n plus 0,
Good. And what is the integer right before that?
and minus 1.
Good. Excellent. So the point is, when you have this kind of expression and you're asked to simplify it, take the bigger number. N plus 2 is bigger than n minus 1. Do you agree?
Yes.
And the reason we look at the bigger number is because n plus 2 factorial, by definition, is n plus 2 times the integer right before that, which is n plus 1, times the integer before that, which is n, times the integer before that, which is n minus 1, times the integer before that, times the integer before that. So the rest of them all just get rolled into the idea of n minus 1 factorial, because n minus 1 factorial is n minus 1 times the number before that, which is n minus 2, times the number before that, which is n minus 3. And we don't really know how far it goes. So we just say, hey, the rest of them, the rest of these factors are actually described by the expression n minus 1 factorial. Does that make sense?
Okay, so
And the reason we stop at n minus 1 factorial is because we know that down here on the bottom, we have n minus 1 factorial. And these are things that are being multiplied together. These are integers that are being multiplied together. So once we get to n minus 1 factorial, which means n minus 1 times all the integers that are smaller down to 1, these two factors cancel. So our answer is n plus 2 times n plus 1 times n. And that'll be true for any integer n greater than or equal to 1.
so
Do you want to do another one?
yes, I think yes.
All right, let's do
You got the
4.
answer for
Let's
the
do 4. Yeah, let's make up another one. 4a prime, okay?
okay.
So what if we have n plus 1 divided by n minus 1 with factorial here and factorial here, okay?
Okay, so it's going to be like and no, let me see.
So which one's the bigger one?
The n plus one.
So that's the one we're going to expand until we see n minus 1.
It's n plus one and and then n minus one.
Factorialized. And
Mm-hmm.
this just means just keep on going until you can't go any further. And then what's on the bottom?
But like n minus one,
Factorial. And then what cancels?
n minus one, n minus
Yeah.
one. Yeah.
You see it? Good.
So we can have like we don't need to write the a number for that. Like,
No, we're just writing these expressions in terms of n.
um,
Let's do one more. Shall we do one more?
yes. It's
Okay. Oh, question?
no.
Okay. What if we have n minus 2 on top and on the bottom we have n minus 1? Now, which one is bigger?
So n minus two and n minus one is
So we expand the one that's larger. So if we expand n minus 1,
n minus two.
yes, good. So it's n minus 1 times n minus 2, and then it would be times n minus 3 times n minus 4, but we don't really know how far that goes. So we just say, hey, the rest of them are expressed with the factorial. Does that make sense?
Yes. So and the top like on the like n minus two factorial and n minus two will be like cancel.
Exactly. Very good. And then what is our final answer?
Minus one.
1 over n minus 1. Exactly. I think you've got it.
Yes.
Good. Hi, Nora.
Yeah, it's making easy now.
Good. Yeah, it is. It is.
Evening.
Good evening. How are you?
Yeah, now
I'm good. Just enjoying this review.
And in fact, tomorrow I'm going to let the class vote on whether they would rather have the lecture on Chapter 7.1 or a review for Test 3. But the agreement is going to be if we have the review during class time, everyone is going to have to watch a video that I'll post on Saturday before class on Thursday.
I
So
vote that.
you vote have the review and watch the video.
Yep.
That's what I figured. And then I've got a nice review sheet that I've put together with some questions, all kinds of questions, and I'll hand this out tomorrow. In fact, I'll probably post it in the morning. But some of these questions are very, very much like measure two material, you know, plus a couple of induction proofs and couple of set proofs. So some partition games. Um, so I'm sorry you don't have access to that right now. Um, but we certainly have access to measure two material right now. And then over the weekend, we'll have office hours and we can have an extra office hour on Saturday if people want, once you get your review sheet tomorrow.
What time is it on Saturday?
Well,
The
somebody has to email me and ask.
okay.
Would you like me to uh, try to share this review sheet, or do you have some questions, Nura, from the Measure 2 material or WebAssign?
WebAssign looked pretty good. Already started working on it. The
Good.
Measure 2 materials for that we just recently gave us. We talked about those, but I would love to talk about more complicated sets, the subtraction and addition and the intersection and union. I'd love more practice with that.
You mean basically set proofs rather than just set calculations or set calculations?
Well, I looked at the class notes from our last class where you had set proofs,
Uh-huh.
and
Uh-huh.
I've been trying to get a feel for how you present the information and where you start. And it seems like the proof centers around the major operator, like if it's an and, like A intersect B union, A intersect C, for example, then
Right.
you would prove the two, I don't know if minor cases is correct, but the two arguments in parentheses around the central operator. And
Yes.
yeah, I'm trying to get this quiz done. I know it's not, an excuse, but I've had so much work and I'm trying to get
Oh,
these
I
proofs
know.
done.
And usually, honestly, usually I give you more time. I give you a week, to put together a take-home quiz. But I really wanted to get people to go ahead and practice. So why don't we look at one of those quiz proofs?
That'd be great.
All right. So which one would you like to look at?
Um, so I started on the first one which is the proof by cases.
All right. So
But
what are we proving? What is the statement? It's for all sets A, B, and C, what happens?
yes, I just got it up. Okay. For all sets A, B, and C, such that A minus B union C minus B is equivalent to
Equal to, actually, because these are
equals.
sets, not statements. So
Oops.
that's fine. No, no, you're good. You're good.
A union C minus B.
Okay,
And
great.
I'm sorry.
No, go right ahead. I'm going to hush and let you talk.
Well, I understand this to be based on the class notes that A minus B union C minus B is a subset of A union C minus B. That's what we're trying to prove.
That's one direction.
And we're trying to prove that A union C minus B is a subset of A minus B union C minus B.
Exactly. We're going to have to prove two subset inclusions, that this is a subset of this, and then turn around and prove that this is a subset of that.
Okay.
That's exactly the right. I know it's a lot. So just let's just take a deep breath, right? And the first thing we do is we just tell the reader, oh, letter A and letter B and letter C represent sets. Whenever we introduce variables, we always tell the reader what they represent. So just you can just start by saying let A, B, and C be sets. And that just kind of gets you settled in. Okay, we're going to talk about sets. And now we're going to prove, it doesn't matter which direction you prove first, okay? I generally prove left to right first because I read from left to right, and then I turn around and prove right to left. But it doesn't matter. As long as we do both of these subset inclusions, we're great.
So what we can't do is start talking about that entire thing.
That's right. You
Okay.
could say we wish to prove
Okay.
that, but we won't just state that as if it's true because that's what we want to try to establish.
Okay.
And it's a fine point, and I'm probably not going to dink somebody real bad if they accidentally state that which we wish to prove. But in general, we're going to prove what we wish before we state that it's true.
But the thing that, oh, I'm sorry, go ahead.
We can always say we wish to show.
Okay.
You can always say, we wish to show that this is a subset of that, and that is a subset of this. No problem with saying we wish. And if you like, are you more comfortable with that?
Yes, because then we can look at it and see what we're doing.
Great. Okay. So let's write what we wish. We wish to show two things, right?
Now, we want to show that X is an element in A minus B union C minus B, right?
We want to assume that if X is an element of A minus B union C minus B, that implies, and ever since we had the discussion about what Epps says about the implies, freaks me out, but it's an if then. We wish to show that if this is true, then X winds up over in A union C minus B, right?
Yeah.
And we wish to show that if X starts out in A union C minus B, then what happens?
Then it is also in A minus B union C minus B.
Great.
It's
So
also an element.
that's right. So sometimes it really can be helpful to just say, okay, I want to write down what I'm trying to do for sure. Like this notation doesn't do it for me, right? And as long as you state it as a wish, that's fine. We can wish anything we want.
Okay.
Okay. But at least now we know we're going to take an X from this set and we're going to use, like you said, the last operator that gets executed if we were constructing it is this big union. We'll break this down first with the union. That'll give us two cases because it's an OR operator. And in both cases, we're going to work to get toward this.
Okay.
Shall we start it?
Yes. So we start by assuming that X is an element in A minus B union C minus B.
Nice job with the reading of the sets. And we could go ahead and write what we actually wish to do.
Is prove that X is an element in A union C minus B.
Exactly. So that even breaks it down a little bit more. Because what we're doing is a direct proof of an if-then statement. We assume the hypothesis and we wish to show the conclusion follows. We are establishing an if-then statement when we are establishing subset inclusion by what's called the element chasing method. It's called chasing elements. We're chasing X around, basically. We're chasing it from this set into this set, and then we're going to turn around and chase X from this set into that set. That's why it's called an element chasing argument, which I don't think I put into the class notes, but I did mention, and it is in the text.
That's cool.
It is. So we're going to chase away. So let's just kind of think about what it means. And we don't want to think too deeply, okay? We want to just keep it super simple, one step at a time. We don't have to unwind all of this all at once. Let's just start by unwinding what this union means because it's kind of the big operator in some sense, right?
Right.
So what does
So,
it mean?
so it means that X is an element in A minus B or X is an element in C minus B
And that's by definition of
by definition of union.
precisely. And the minute we see an or, or means cases.
But we've already defined our cases on either side of the or operator, right?
We sure have. And that's real helpful because that tells us what we're going to assume in each case.
Mm, okay. So I wrote out your class notes just to kind of get a feel for this. So we start with so since X is an element in I'm sorry, case one, we would say.
Exactly. We want to parse out our cases. So suppose or let or assume. I like suppose inside cases. I don't know. It's a matter of taste. But what should we suppose for our case one?
Suppose X is an element in A minus B, then by definition of minus,
Yep.
X is an element in A.
So by definition of, and I'm going to say set difference, but if you said by
Okay.
definition of minus, I wouldn't take off. I think in WebAssign it says by the laws of set difference, which I kind of hate. I kind of love to hate that. But anyway, by definition of set difference, what do we?
X is an element in A, and X is not an element in B.
Perfect. And there's not much more we can do from there. Let's just hold that thought. These are called atomic statements. You see, we could break down the statement that X is an element of A minus B because there was an operator involved. But once we have broken it down to X is in A and X is not in B, unless we're playing like set complement games, we can't do much more with this right now. So let's just hold that thought and let's go to case two and see what it gets us. Or we can look and see what we're trying to get.
Um, I guess Kate, well, what should we do?
Well, that's a really good
Case two?
question. Let's do case two and then let's see if we can kind of break down our wish to see
Because
what
we
it's.
don't have enough information to look at that yet because we don't have C.
All right, let's look at our case two. So what is
Um,
our
s-
supposition for case two?
Suppose X is an element of C minus B,
Great.
then by definition of set difference, X is an element of C
Mm-hmm.
and X is not an element of B.
And some people like to say but there, but it doesn't matter. You can say and or but this would be a perfect time to say but if you wanted to. Because we usually say but when there's something in the affirmative and something in the negative. That's kind of when we usually say but. Like, hey,
Uh,
I like pizza, but I don't like anchovies, That's when but usually, but it doesn't matter. And is perfect. Let's let's
I'm
unwind
sorry,
our
go
yeah,
ahead.
no, let's look at our wish now so we can kind of figure out how we can connect where we're at with where we want to go.
Okay.
So
We
what do we
wish
really wish?
we wish to show X is an element in A union C minus B.
Okay, let's get a little bit more into that. What does that really mean?
That X is an element in A and X is an element in C and X is not an element in B.
All right. So I noticed that you changed The wording, instead of saying X is an element of A union C, you went ahead and started to put words in for union. I would discourage you from doing that right yet. First, just take this whole thing as a big bite. X is an element of A union C, and X is not an element of B.
Oh,
And then in the next, if you want, we could say, we could expound a little further and break down this. What does X is an element of A union C mean?
that X is an element in A, or X is an
Well,
element in C.
and then a
It
big
does.
comma because these have to be separated. These are grouped together, so we use commas. Remember when we have ors and ands in the same statement, we separate them with commas, and X is not in B. You see, and we're already at this place right here because in case one, we have X is an element of A. Well, then it's going to be an A union C by definition of union. In this case, we have that X is in C. So we'll be able to say, hey, X is in A union C by definition of union. In each of these cases, we'll be able to argue that X is an element of A union C.
So now we write our argument for this part of the proof that it's true.
Uh-huh. Yeah, it's kind of like we've reached the halfway point. We've broken down what it means for X to be in this set to its atomic parts. And now we're trying to build up to this, but we're kind of working backwards to see how we're going to get there.
Ah,
Now, there are a couple of different ways we could approach this. Inside each case, we could actually write one more sentence and say X is an element of A union C because we have that X is in A. So by definition of union, X is in A union C. We could write that here.
ah.
And in this case, we could go a little further and say, hey, X is in C, so X is in A union C by definition of union. We could write that here and we could write that here. But we don't have to put it inside the cases. What we could do is just realize, hey, since X is an element of A in case one, and X is an element of C in case two, what could we say? Then
Then X is an element in A. Oh, here it is. A minus B. Wait, oh no. X is an element in A union B. Oh, C. I'm sorry.
you're fine by definition of
Union.
union. So we've got in both cases that we had enough to get X into A union C. But also in both cases, we still have that X is not in B. We also know X is not in B in both cases. And so now we're headed back to this. So we got from here to here, and now it's one step to get X in there. Because now we do have that X is in A union C, and we still have that X is not in B. And so it's just like one more sentence to get X where we really want it to be.
Ah.
Do you see it?
So we don't have to do another round of proof by cases for the second statement.
We sure do not.
Oh.
So now X is an element of what?
A union C. Minus B, I think we're doing the entire thing.
Mm-hmm. By
Since,
definition,
oh, by definition of, should we say union and difference of sets?
we
Or
already
just,
used definition of union here when we got X in A union C. Now we're
Okay.
using the fact that X is in A union C and X is not in B to introduce this operator. So it's really by definition of this operator at this stage of the game.
By definition of difference of set differences.
Yep. And that's what we wanted. So what did we just show? We showed that if X is an element of A minus B union C minus B, then that implies that X is an element of A union C minus B. And that means that A minus B union C minus B is a subset of A union C minus B by definition of what?
Of subset?
Exactly. And that's half our proof. Now, like I said, that's not the only way to write the proof. What we did here to get X in A union C, we could have done that here, and we could have done it here, so that by the time we get to this stage, we would already have had that X is in A union C, and X is not in B in both cases. You see what I mean? So that's just a matter of choice. But my recommendation is just to be real careful. And when you're breaking down and building up, do it one operator at a time. Like, don't try to go from X as an element of A union C minus B to this, go through this. See what I mean? Like, don't try to do the and not at the same time as the or. Try to kind of break it down into two phases, especially since technically and truly, when we have a sentence, and this is true in English as well, when we have a sentence that involves an or as well as the and, we really do have to use commas to indicate what's happening kind of together and what is separate. You know, these two are separated from each other, but these two are grouped together, and that's indicated by these commas that tell us the and operator is being, the and for this set difference is happening kind of last. That's what the commas are like parentheses.
Oh, okay.
But in a weird way. It's not parentheses around the and, it's parentheses around the stuff on either side of the and. Even though we don't usually put parentheses around X is not an element of B, technically it's this is grouped with this, and this is grouped with this, with itself.
Oh.
That's really what the commas mean. So I don't want to ruin all the fun for you, but that is half of it.
So now we have to turn around and prove for X is an element in A union C minus B is this oh no, that's not it. A union B, no, A union C minus B is a subset of A minus B union C minus B.
Right. So we would start with X in here, and then we wish to show that X is over in this one. And, eventually this, you'll break down the set difference first. But when you break down the union, because X will be in A union C, that'll be two cases. Either X is going to be in A or X is going to be in C. But when X is in A, it's also not in B, you'll get it into A minus B. In the case when X is in C, it's not in B either, you'll get that X is in here. But if X is in here, it's in the union by definition of union. If X is in here, it's in this union by definition of union. And you'll be faced again with the choice of whether or not to work through the entire thing, and you wind up kind of doubling what you say because you kind of say it twice when you get that X is in this union, or you can get that X is in A minus B in one case, then in the other case, get X is in C minus B, and then outside of the cases, say, hey, we've got X in A minus B in one case, and we've got X in C minus B in the other case, but that puts it in the union of A minus B, union C minus B in both cases by definition of union. Once because it's in there, the other case because X is in there. But in both cases, it winds up in the union because the union's the or. See what I mean? Like, so there's still going to be a style choice. Union proofs are the most difficult ones for sure.
Wow.
But I hope that that gets you well started.
Oh yeah, this is great. I appreciate it.
You're very welcome.
It's hard to be so concise and only show what you need to show.
That's right. And if you are a little bit redundant, better to be a little redundant than to leave things to your reader's imagination.
Just writing that down.
It's better to say a little too much than to say too little because you just want to make it so simple that when you read it, it's like, oh yeah, that follows from what I just said. And oh yeah, I can say this because I just said, the thing right before, so that there is no question. Like what you don't want is the reader to say, where did that come from? Sunita, it's your turn. Do you have a question?
Yeah, I think yeah, it's from same from the review said. So yeah, I've been doing like this, I remember. But I think I'm also confused on the like five,
Which problem?
the question number five is
Okay. Ah, partitions. Let's just review what a partition is. Given a set A and a collection, I usually call it curly C. Say A1, A2, dot, dot, dot. Say up to A sub K, but it could be infinite. This dot, dot, dot could be forever. Of subsets of A. Each of these is a subset of A. These are called the partitioning sets.
you talking?
Oh, I'm so sorry. Was I on mute that whole time? I apologize. So, given a
Mm.
set A and a collection, curly C, with sets A1, A2, dot, 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 up to A sub K, of
Mm-hmm.
subsets of A, these are called partitioning sets, these little subsets. We say this collection, curly C, is a partition of A if three things happen. Each of these A sub i's is not empty. If we take any two of these, like A1 and A2, and look at their intersection, that is not going to be empty. Or A1 intersect AK, or A2 intersect A3. Any two of them, if you take any two of them and look at their intersection, that, should be empty. Sorry, it should be empty. Did I say not empty? It needs to be empty. And that's whenever I is not the same as J. Now, like if you take A1 intersect A1, that better not be empty because A1 is not supposed to be empty. But if you take any two different sets, and we indicate that by giving them different indexing numbers, I and J, their intersection should be empty. None of these should have any elements in common with any of the other sets. And then finally, the union from I equals 1 to K of these A sub i's should be all of A. In other words, if you take the union of all of these, that should give you the whole set A. Do you have any questions about the definition of a partition?
No.
So there were some WebAssign problems where you were asked to, look at partitions.
Okay.
Did you work any of those WebAssign problems?
The 6.1 I missed because it was like I was doing and then at like almost like 11:50. I mean, and then after like a couple minutes, the due date is like expired, and then now,
I gave you an extension.
and then the 6.2 is I'm working now.
Okay, but did
Like,
you put in a request for an extension for
yes,
6.1?
I did, but it wasn't.
Okay, I just saw that. So yeah, um, I was really busy all day, so I didn't see that until just a little while ago, but I've given you an extension on 6.1 as well. But
Okay.
let's just work through, maybe some examples, and then we can look at the actual problem on the review sheet. Okay. But let's say that our set A has these elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. So for A, let's let this collection be the set that contains 1, 2, 4, and 6, and then 3, 5, and 8, and then 7, 9, and 10, for example. Okay, so this is our set A1, this is our set A2. Even though it's not written there for you, you could label these set A1, A2, and A3. So let's just check. Is this collection, curly C, a partition of A? Okay. Well, we've got to just double check. None of these are empty, right? This isn't empty, this isn't empty, and this isn't empty. So property 1 of a partition, which requires that none of those sets be the empty set, is satisfied. That one is never going to go bad, I think. So 1, A1 is not empty, A2 is not empty, and A3 is not empty, check. You could always name these. Even if I didn't name them, you could say, hey, I'm naming this one A1, this one A2, and this one A3, Then we have to check the intersection. In other words, if you scan through here, we're scanning to make sure no element of A appears in more than one of these sets. So when you scan through there, is there any element of A that appears in more than one of these sets? In other words, if you take any two of these sets and look at their intersection, like A1 intersect A2, is there anything that's in A1 and in A2? We're checking that right now. And then we're going to check if there's anything in common to A1 and A3. And then we'll check to see if there's anything in common to A2 and A3. That's the same thing as just looking to see if there's any element that appears in more than one of these sets. So what does A1 intersect A2? Do they have any elements in common? Sunita, are you there? Nura, what do you think? What is A1 intersect A2?
It's an empty set?
It is empty. There are no elements that appear in both of these. Sunita, are you with us? She might have had to step away for a minute.
Oh, yes.
Okay. Do you understand what's happened? Did you have to step away? Did you hear what I just said?
Hmm.
So do you see that A1 and A2, these two little partitioning sets, they don't have anything in common, right? There's no element that appears in both of these. So their intersection is empty. Do you see that?
Hmm.
Well, now we're going to check A1 intersect A3. Do these two sets have any elements in common?
No,
So what is their intersection? What is A1 intersect A3?
the empty.
It is. And then we look at A2 and A3, and they have nothing in common. So check, check, and check. These are mutually disjoint sets. That's what's required. That's what mutually disjoint means. Mutually disjoint doesn't mean that the intersection of all of them at the same time is empty. Mutually disjoint means if you take any two of them at a time, their intersection is empty. And of course, the intersection of all three of them is empty, but that's not quite the same thing as mutually disjoint. And that's one place where the book falls down in WebAssign. WebAssign isn't very good about that. It's not that it's wrong, it's just that the way that the exercises are designed can lead to a misunderstanding about what mutually disjoint means. Mutually disjoint doesn't require that we intersect all of them and ask if that's empty. Mutually disjoint says we have to look at them two at a time. And that's why we also call this pairwise disjoint. I like the word pairwise better because that reminds us we're looking at the intersection of two at a time. And then the last thing that we're going to check is if the union of all of these three sets, because there's only three of them, if there were four, we would union them all to check if that's the whole set A. So if we take A1, union A2, union A3, do we get all of A back? Well, let's see. 1 is in there, so I'll write 1 down. 2 is in A1, so it's in the union. 3 is in A2, so it's in the union. 4 is in A1, so it's in the union. 5 is in A2, so it's in the union. 6 is in A1, so it's in the union. 7 is in A3, so it's in the, see what I mean? Like we're checking to make sure that every element of A appears in exactly one of those. That's basically what it boils down to. This collection is a partition of A if each element of A appears exactly once in one of the partitioning sets, and it does. So the answer is yes. It is a partition of A. Does that help?
Yes.
So we can do another one. We can use the same set A and we can let our collection be this collection. 2, 4, 6, 8, 10 could be in one set. 1, 3, 5 could be in one set. 7, 8, 9, 10 could be in another set. Is curly C a partition of A? We have the same three things we have to review. We have to verify. I saw the word review and I said review. That we have to verify. We have to see that each one of these is non-empty, and we can name them. We can call this A1, we can call this A2 just to make our life easier, and this A3. Each one of those is definitely non-empty. So A1 is not empty, A2 is not empty, and A3 is not empty. So check, check, and check. They're all not empty. Great. Now we're going to look at the intersections. Are these mutually disjoint? Are these pairwise disjoint? What do you think?
Mm, It's mutually disjoint.
Yeah, that means if you take them two at a time, is their intersection empty? Another way to think about it is, do you see any element of A appearing in more than one of these sets?
Yeah.
Okay, so tell me exactly what you see appearing in which two sets.
The A1 is like 8, 10,
So A1 intersect A2 has 8
and
and
10.
10 in it, and that's not equal to the empty set. So this is not a partition because this property failed. The union property, I think, is satisfied. I think A1 union A2 union A3 is A, right? Because 1, 2, 3, 4, 5,
Excuse
6.
me, Professor.
Yes.
It should be A1 intersect A3.
Oh, thank you so much, Nora.
Actually.
Thank you. I need that help at this time of night. So two of the properties hold, but that's not enough, is it? The fact that AI intersect AJ was not empty for an I not equal to J, because indexing number 1 is not the same as indexing number 3, right? Here, I is 1 and J is 3. So it fails to be a partition. Okay. There's another way it could fail to be a partition. It could be short. It could be that uh, they're all non-empty and they're pairwise disjoint or mutually disjoint, but we might just fail to have one of the elements of A in any of these. So this last property could fail. Does that make sense?
Yeah.
Like we could rework this example and disappear 5 from A2. And then this could fail for this reason. But I mean, we could just, make one more example. I don't know, do we need to make another example so I can show you the other way it could fail, or do you understand?
I mean, like, I feel like I understand, but if you go with another example, it will be better.
So it's going to be the same A. And here's our collection. 1, 5, 6, 10, 2, 3, 4, 8. Okay. Is curly C a partition of set A? Well, the first two properties are going to be okay. A1 is not empty. We can call this one A1. A2 is not empty. A3 is not empty. They're also pairwise disjoint, right? A1 intersect A2 is empty. A1 intersect A3 is empty. A2 intersect A3 is empty. Check me on that. Is it true?
And
Are there any elements in common to A1 and A2? Nope.
no.
Any elements in common between A1 and A3? Nope. So it's empty. A2 intersect A3? Empty. But if we take the union from I equals 1 to 3 of the A sub I. In other words, if we look at A1 union A2 union A3, what is in the union? Well, we've got 1, 2. I'm just putting them in order. You don't have to. 3, but it makes it easier. 4. What else is in there?
5, 6, and 8, 10.
And that is not equal to A because we're missing a couple of elements. We're missing 7 and 9. All we have to be missing is 1. Like we could change this and make it the set containing 8 and 9 even, right?
Yes.
And it would still go bad. And now darn it, why did I do that to myself? Because now I've made it so that I can't write it all. But anyway, I make it skinny union. Everything but 7 is in there. 1, 2, 3, 4, 5, 6, no, 7, 8, 9, 10. The point is, just having one missing element is enough to make it go bad on property 3. Okay. Now, on the review sheet, we had some more interesting sets because one of the sets from the review sheet used interval notation. Two of them did actually, right? On problem uh, number 5. On number 5, B, A is the unit interval from 0 to 10. So this is an infinite number of real numbers, not just the integers from 0 to 10, but there's like 1/2 is in there, pi is in there, 2 pi is in there, 34/59 is in there. All kinds of numbers are in there, not just the integers. And we defined a sub k to be square bracket k minus 1 to k. And this is for k equals 0, 1, 2, up to 9, I think, right? Up to 9. Is it 9?
10.
It needs to go to 10, doesn't it? Well, I made it go from 1 to, I made it go from 1 to 9. That's fine. We can work with that. It can make us be careful. And the collection was the set from A1, A2, up to A9. And the question was, is this collection a partition of A? It's fine that I only made it go up to 9 because it actually makes it go bad 2 different ways. Well, the first thing we do is we check each of these A sub i's to make sure they're not empty. Well, A sub k is not empty because, well, let's just look at A sub k. It for sure has 2 elements in it. It's got the integer k in it, and it's also got the integer k minus 1 in it. So k minus 1 is an element of A sub k, and also k is an element of A sub k. And if you wanted to split hairs, or even get more interesting, the integer between k minus 1 and k, like k minus 1.5 is in there too. The average of these two numbers is in the middle there. I mean, it's got a lot of, none of them are empty. Do you understand that?
Yes.
But what about empty intersection? Is AI intersect AJ equal to the empty set? What do you think?
AI.
Let's draw these. Let's see if we can draw a picture. Here's 0. Here's 1. This is square bracket from 0 to 1. That is A1 right there. Because A1 goes from 0, 1 minus 1 to 1, right? A1 equals 1 minus 1 to 1, which is square bracket 0 to 1. So that's that's what A1 is. Let's look at A2. What is the interval A2?
1 minus 2.
2 minus 1
Yeah,
to
2.
2. So it goes from what to what?
1, 2.
Good. So here's A2, but it's square bracket. When we intersect A1 with A2, what do we get?
1.
Yeah, the number 1 is in both of them, and that is not the empty set. So this fails. You know, this part is okay, but the property 2 fails. And also, if you miss that, when we take the union, A1 union A2 union dot 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 up to A sub 9, we're starting with 0, 1, but we're only going up to 8 comma 9. That was actually a typo on my part, but it's fine because that is not equal to A, right? What is it equal to if we take the union starting with A1 going up to A9? What is that union really going to be?
10, 0.
0, 2,
It's like
it only goes to 9, and that's not equal to A because I only put it up to 9. So the last interval that we're unioning together goes from 8 to 9. That's A9. I would have needed to make it go all the way to 10 for us to get all those missing numbers that are in A but aren't in this union that only goes from 0 to 9. Do you see that?
yes.
So it fails, 2 different places. Nuri, your turn. Do you have a question?
Yes, so just for clarity's sake, this problem that you're working on right now, A is the universal set, AK is the last value or like the sequence value. So that's the sequence we use to solve for the values in the set A.
That's right.
And then C is the collection of this of A at partitioned at each value of K.
That's right. But I only went up to 9. I actually kind of meant to go up to 10.
Oh,
But it's okay because it still is a problem. The point is if we wanted this union to be all of this, we would have had to go up to A sub 10, but I only went up to A sub 9.
okay.
But that's okay. It could be a different problem where I do go up to 10, but it's still going to fail to be a partition, not because property 3 fails, but because A1 intersect A2 is still not empty. And
Ah,
A2 intersect A3 would still not be empty. It would still fail to be a partition, but not because of 3 failing. It would fail because of 2 failing. And like I said, that
okay.
was actually a typo, but I may change that.
Okay. I struggle still a little bit with the set subscript notation and the just interpreting all of the
Indexing,
things. Indexing.
indexing, indexing and we have really tried to dig into indexing, and we have several different applications. We have indexed summations, where we have the sum from I equals, something, say little a up to little b of some term, C sub I. And we have a product. And this is where A is less than or equal to B because we don't want A to be bigger than B. We have product notation where we start from I equals, oh, I wrote a sum, but I meant to draw a product. We have a product from I equals, some lowest level integer value up to some upper level integer value of some term, C sub I, where we have a definition for the term C sub I. But now we have unions, where we're taking the union of some term C sub I from I equals A to B, where A is less than or equal to B. And we have intersections. And sometimes those can even go up to infinity, right? And theoretically, you could have there are sums to infinity. In fact, that's a thing. Sequences are the terms when they're listed with commas between them. When you put pluses between them, that's called a series. And we don't really get into that lingo in this class, but in calculus you do. And one of the big questions we ask is which series converge? In other words, which series head toward a particular value as you add more and more values, and which ones do not? Which ones diverge? But yeah, the point is this term, C sub I can take many forms, right? But the thing that is usually true is C sub I is a function involving I. It's some expression involving I. C sub I could be I squared minus 3I. Or, C sub I could be negative 5 raised to the I, right? Or C sub I, could be 10 plus 5I, right? Non-arithmetic, non-geometric. This is geometric. This is arithmetic. We could say for I greater than or equal to, I don't know, you can start it wherever you want. Say 2. Here for I greater than or equal to 0. Here for I greater than or equal, to 0 if you want, or 1, or whatever. C sub I could be I plus 1 factorial divided by I minus 2 factorial. And this would only make sense for I greater than or equal to 2. Maybe I'll make this one a 1 just because the other ones are different. So the point is, whatever sits here in the sum or the product or the union. Now with its union, it's not going to be terms like this. This is for products and sums. When we are playing indexed games like this, I should actually make these capitals. You know why? I should make these capitals because these are always sets. These are just expressions like these. These are sets. So for sums and products, oh, I hate the ampersand. Avoid the ampersand. For sums and products, the little c sub I can take many forms, but it's a function. When c sub I for unions and intersections, C sub I is a set defined in terms of I. And, some examples would be like, C sub I is the closed interval from I to I plus 1. Or C sub I could be the closed interval from negative 1 over I to 1 over I. And maybe it's soft brackets. Maybe C sub I is -1 minus I. Oop, I want to make soft brackets. To 1 plus I, soft brackets. Or maybe it's a Clopin set where it, is square bracket on one side and soft bracket on another side. See what I mean?
Oh,
The deal is no matter whether the application is with sets, this is all interval notation sets. Interval notation, no, sets in interval notation. Whether it's that or whether it's just expressions because it's a sequence situation, we're thinking of terms of a sequence. It's a matter of plugging in the value for I wherever you see the I. Okay. Or K. If it's a K, there would be K's here. If it was J, we might use J, and then there would be J's instead of I's. See what I mean? Whatever indexing variable you choose, that variable turns up in the expression. Doesn't have to be I's. It could be K's or J's or N's. We've
so
seen, go ahead.
when you were discussing partitions earlier and you used AI is not equal to AJ, that would be two different sets and their intervals.
Yeah, when we say I is not equal to J, so basically in the partitioning, part 2 definition, we could say if I is not equal to J, then we want A sub I intersect A sub J to equal to the empty set. This is what it means to say A sub I intersect A sub J equals the empty set whenever I is not equal to J. We didn't really study this form as being equivalent to if then, but it is.
Um,
These mean the same thing. This is an A sub I intersect A sub J equals empty if I is not equal to J. That's really what that means. So it isn't if then, but it's written kind of back assward.
so A sub I and A sub J are their pairwise sets.
That's right.
Okay.
And we are saying these are two different sets and the way we say it is by saying the indexing numbers are different, and that lets us know we are only trying to intersect two sets that are really distinct from one another. That's what the I not equal to J means. This condition tells us we are looking at two different sets. That's the way that we express that idea mathematically. Because we assume we're not going to be naming one set with two different indexing letters.
Hmm.
That's the underlying assumption. Like, we wouldn't call A1 equals the set containing 1, 2, and 3, and then call A2 the set containing 1, 2, and 3. We wouldn't use different indexing variables if we were talking about the same set.
Ah.
And so this is the way that we express that. And I'm sorry if I did not really make that more clear when I introduced partitions.
Sometimes there's so much going on in these expressions. It's just like
Well, what we're learning to do is read mathematics, and there is a lot going on. You said it. There's a lot going on, and it's a lot to learn, but some of the basic things are happening right here. Because, for example, if you set up a loop, you're going to have an indexing variable that counts iterations in the loop. You may even have nested loops, a loop within a loop, where you have a couple of different indexing variables being incremented, okay? And what is happening inside the loop actually might be using the indexing number as part of a formula in what is being executed inside the loop. So like when I is 3, that value 3 plays into whatever kind of calculation is happening during that iteration of the loop. Then I gets incremented to 4, and then when the loop is executed, the 4 is now the value that is going to come into play as that loop is executed, et cetera, et cetera, et cetera. A lot of times, the reason we set up a loop is because we want to do a sequence of calculations with an incremental value, a value that increments. I mean, that's a lot of times that is the motivation for setting up a loop. It's not just that we want to do something 100 times. It's that we want to do it 100 times, but we want to do it for different values of k. We want to do it for when k is 1, and then for when k is 2, or when k is 3. See what I mean? And we want to just write one piece of code that executes that operation for these different values of some variable, and that is our indexing variable. Maybe we want to increment by +5. We want to do it for when k is 0, then when k is 5, and then when k is 10, and when k is 15. Well, that is still a loop situation, and the loop can be executed many times, but inside that loop there's a variable that's getting incremented by a larger amount than 1 every time the loop is executed. You could say, hey, I've got a variable inside the loop where I'm going to let it be k plus 5 from whatever the prior value of k was. And that way you get an incrementing by +5, +5, +5, inside a loop where I goes from 1, to whatever, 100. Well, every time this increments, the k increments by 5 inside the loop, and then you end your loop. So it's like a 4, I equals 1 to 100. Do let your k, you start, you initialize k, some initial k is like k equals 0, and then you would start, doing, k squared plus, 3k minus, 8 or something equals some value m, print m or something. I don't know. The point is, you might have nested loops where there's an incrementing in a standard way, but then inside the loop even you might have a different kind of incrementing. You'll find you'll run into it in coding.
Yeah, sometimes it's a little hard to realize that we're talking about the same thing, but in different ways and with different depths of analysis. So I see this is the index of the encoding structures. Okay.
Yeah. Yeah. I mean, the idea is just to learn how to read and substitute sort of in a basic way so that when you really have to start using it, it's not a completely foreign concept. Have you done any loops yet in your coding? You've taken 236, right?
I have. I can actually write Python and Java loops. I understand the concept, and it's just tough sometimes to, I guess, the energy. I'm tend to be exhausted to realize that this is all we're talking about the same things. And
Well, but it is exhausting because what we're talking about in this class is sort of so abstract and general. Even though we have specific examples, the idea really in this class is just to help teach you to think logically, to learn to read, learn to think carefully, learn to check, have I covered all my cases? And just to learn to think in a logical sequence of steps. This is sort of like training. It's like, I don't know if you ever played piano or any instruments, but you learn to play scales, and that, teaches you to have fluidity. And then once you've got all these scales, then it's easier to play real music because you have your fingers are nimble enough to move, and you're familiar with basic chords, if you're playing guitar or something, or soccer moves, when you're out there in practice, you're just learning to dribble the ball and pass the ball but then when you get in the game, there's a lot more going on, but the basic kind of structure of being able to perform those basic operations makes it easier to do higher level stuff, supposedly. That's the hope anyway.
I see, and it is helpful. It really is. I'm hoping when I get through these classes and I have a minute to kind of think about what we've done, then a lot of stuff will click. But it really is interesting and helpful.
Do you think, I'm kind of thinking about asking my students to buy the hard copy of the book because this is a great reference book for later. I hate that you lose your access to this great book after a year. I really think, I may at least just encourage kids to go online and for $20 get a used copy of the book. Doesn't even have to be the latest edition, but just to have the hard copy as a reference book. It's a great reference book. It really is.
I actually plan to download all of your uploaded notes in class, office hours, and things like that. And what is the title of the book? I'd be interested.
Yeah, right. It's in the syllabus, but it's discrete mathematics with applications, and there are a bunch of editions. I kind of like the third edition. We're on the sixth edition, I think. This is edition, and her name is Susanna Epp, EPP. She's the author, and I think we're on edition six. I actually like the third edition a lot, but there's nothing wrong with the sixth edition, and there are actually some typos in the earlier editions. We're either using edition five or edition six. I honestly don't know because I just use an old edition if I want to look at the hard copy. But you don't have to buy the latest edition. If this is the latest edition, buy edition five or edition four. You can get a used one for like $20.
That sounds good.
It's a really, buy used, I would love to see us move away from ebooks. I like the WebAssign, and the ebook has to kind of come with it because you've got to be able to, poke around in the book. If you say, take me to where, the information is, it has to be linked to the ebook. But I really do think having a hard copy book is a huge advantage. Just, being able to mark pages and put notes and put post-its and an index that you can actually use, at the back of the book.
Yeah.
Indexing textbooks is an art, and it's becoming a lost art with electronic books. And an index is such a handy thing. Okay, well, sorry, I chased a rabbit down a tunnel here. Do you have other questions?
No, thank you. A lot of what I need to do is just get the time to practice and read the book. So that's what I'm gonna try to do.
Yeah, and tomorrow we will have a whole, 75 minutes focused on practicing and answering questions. And then hopefully this weekend, you can devote, a chunk of your weekend. Hopefully you don't have a gazillion tests next week.
No, I have a test tomorrow. That's why I wasn't able to complete the measure two material. I wanted to write it up and send it to you. I wasn't able to do that. I have a calculus test, not calculus, trigonometry test tomorrow. So a lot of my
Okay.
time went there.
All right. Well, you get to that. And I have Man, I spent like 3 hours this morning trying to type up the solutions. Let me just show you what this entails. Oh my God, I have to share this with you. I'm so sorry, but I am going to subject this to you. I want you to see. No, really, you've got to see because I don't want you to think that it's called a tech file. It's LaTeX. It's a typesetting program. It's a program. It's not a word processor. Okay,
Oh, wow.
see, I'll make this bigger so that you can see the code that I use to type up this stuff. Okay, so a lot of it but it's math, and then I try to make it in blue, and then I try to align stuff and do formulas, and it is like really involved. So here is how far I have gotten with the solution set, just because it's taking so long. But I have
Wow.
started. But yeah, it's a typesetting program. Like if I make an IO table, like or a truth table, like up here, I've got my little template for making a table, you know, and
Oh
all
my
you have to
goodness.
call all these packages and then I'm always like there's always like a parenthesis somewhere that keeps it from compiling. But I am working on getting the solutions up to the measure two material. I'm gonna sit up tonight and work for another hour and try to get some more of this knocked out. But
Wow.
it really it's you know what I mean? Like this takes some. I really do work hard, and you'd think that I would have had all these already done, but I keep making up new problems every semester because I don't want people to find old problems and just copy the solutions. Anyway,
Oh,
it's like a thing. Okay.
wow.
So, anyway, so thus is life. We all have our crosses to bear, right? But like
Yeah.
this makes fractions look really good, and when you do the binomial theorem, like n choose r, there's a command for that. There's commands to do all that stuff. Anyway,
Wow.
so it's programming, but it's programming to type up math.
That is really impressive.
It makes it look good though.
Yeah.
It makes it look real professional. Anyway, I think I bit off more than I can chew. I think I gave one too many problems on measure 5.1 material. I think I went too buck wild. I gave you every possible kind of sequence, and I think I went a little bit too buck wild on it.
Wow.
So don't feel bad if you don't do them all. But I'm
I'll try
almost
to this
done.
weekend in
Okay.
preparation for the test. I'll try
Well,
to.
let me just say this. Attack the problems that you know you really are having a hard time with. Like some of
Okay.
this will turn into kind of remote work, like the rote work, where it's like, oh, I know how to do this. I'm just doing more and more of it, right? But attack the ones that you don't understand. And I'm going to keep, like I said, I'm going to keep working on getting these solutions typed up. All right. Good night. I'll stop
Thank you.
sharing.
Thank you, Professor. Have a great night.
Good night, Sunita. I'll see you soon.
Hi.